Compressed air is used for many purposes in industry. Powering pneumatic tools is one example. Compressed air can be used to drive grinders, presses, drills, and impact wrenches. Compressed air can also be used to control various types of equipment. Let's look behind this panel. The spaghetti back here is made of dozens of air lines that run to the control panel and then to equipment like air-operated valves or the adjustable vanes on a forced draft fan. When air is used to power or control equipment, it has to be compressed. And that means we're raising the air's pressure above normal atmospheric pressure, giving it energy that can be transferred to a piece of equipment to perform useful work. To raise the pressure of air, we use a compressor. Now, I have one example right here. It's a small compressor, but it works just like some of the larger types that we'll see later. This part is actually the compressor. Over here is the motor to drive the compressor. And down below is the air tank, or receiver, that stores the air that's been pumped out by our compressor. Air compressors come in many shapes and sizes, and we're going to be talking about 7 different kinds of air compressors. We'll see how each type works and look at some of the accessory equipment that's typically found in a compressed air system. In general, air compressors come in 2 basic categories: positive displacement and dynamic. This reciprocating compressor is one example of the positive displacement type. In positive displacement compressors, air is drawn into an enclosed pocket and squeezed by some mechanical force into a smaller space. Then the compressed air is discharged. Dynamic compressors work differently. Now, this centrifugal compressor is one example. It has an impeller that draws air into the casing and accelerates it by slinging it out towards the tips of the vanes. This fast-moving air is pressurized when it slows down on the discharge end. Those are the 2 general types of compressors: positive displacement and dynamic. Here's the basic difference. In positive displacement compressors, air is trapped in an enclosed space and squeezed by some object that displaces or takes the place of the air. Squeezing the air into a smaller space raises its pressure. In dynamic compressors, air is drawn into a space and accelerated. The speed that's imparted to the air gives it extra energy that's converted into pressure when the air slows down. Positive displacement and dynamic compressors also differ in their typical capacities. For compressors, we measure capacity in 2 ways: flow rate and discharge pressure. Flow rate is a measure of how much air comes out of the compressor in a given amount of time. Now, it's typically expressed in cubic feet or cubic meters per minute. Dynamic compressors tend to have a higher flow rate than positive displacement types. Discharge pressure is how tightly the air is packed together when it leaves the compressor, and it's measured in pounds per square inch or kilopascals. That's a metric unit. On the average, positive displacement air compressors can generate higher discharge pressures than dynamic types. Most compressors are labeled to show their rated capacity. The label shows the compressor's maximum rated flow rate and its rated discharge pressure. So far, in looking at positive displacement and dynamic compressors, we've talked about how they differ from each other, both in method of operation and in typical rated capacities. Let's turn that around now and see how these 2 types of compressors are alike. We've seen that both types raise the pressure of a mass of air by adding energy. Positive displacement compressors add energy by squeezing the air. Dynamic compressors add energy by speeding up the air. In either type of compressor, some of this energy is wasted, and that inefficiency shows up as heat. To demonstrate this heat inefficiency, I brought along these items: a bicycle pump, tire, and a thermometer. Now, a bicycle pump is basically a small positive displacement compressor. Air is drawn into the cylinder when the handle is pulled up, and it's squeezed together and discharged when the handle is pushed down. Now, this thermometer will show what happens to the temperature of the air while I pump. And as you can see, it's reading about 80 degrees. Now that we've reached the proper pressure for the tire, you can see that the temperature is about 95 degrees. Any compressor heats the air when it raises its pressure, and this can lead to two different kinds of problems in an air system. The first kind of problem relates to the action of the heat inside the compressor. Many compressors use oil for lubrication, and excess heat can break down the oil, or in rare cases, even set it on fire. When oil breaks down under heat, it loses its lubricating properties and leaves carbon deposits on valves and other internal parts of the compressor. The other problem is that air expands when it's heated. It takes up more space. That's exactly what we don't want in a compressor. We're trying to compress a large mass of air into a very small space. And if the air is cooler and denser, we can pack a larger mass of air into the receiver. There are basically two ways to cool a compressor: air cooling and water cooling. Air-cooled compressors have fins along their cylinders or casings to provide additional surface area for air cooling. Water-cooled compressors are surrounded with a water jacket. Cooling water circulates through the jacket, picks up the heat, and removes it. Some compressors are also equipped with aftercoolers. Air discharged from the compressor passes through a bundle of tubes surrounded by a flow of water. The water removes heat from the air before the air enters the receiver. Those are the two solutions used to reduce the heat of compressed air: air cooling and water cooling. Either kind of system will reduce heat buildup. However, cooling creates a problem of its own: condensation. Normal atmospheric air always contains some moisture. That's what we call humidity. Warm air can hold more water vapor than cool air can. So whenever air is cooled, water condenses into droplets on the cool surface. Here's an example of condensation that I'm sure you've seen before: an air conditioner that drips. When warm air comes in contact with the cold coils, water vapor condenses on the coils, forming drops of liquid. In a compressed air system, these water droplets can cause trouble. Water can damage an air system in three ways. It can wash away lube oil, it can cause rust, and it can prevent air-powered tools and controls from operating efficiently. To prevent these problems, we have to remove water from the air before it enters the receiver or goes into any air lines. We take the water out of the air with a moisture separator. Most moisture separators work by spinning the air around in a tight spiral. Water, being heavier than air, is thrown to the sides by centrifugal force. The water that accumulates in the moisture separator is drained out from the bottom. All air compressors have the same problems with heat and condensation. Almost every compressor has some kind of cooler and moisture separator. Now, that's one of the ways that positive displacement and dynamic compressors are similar to each other. We've also talked about some of the ways these two types of compressors differ from each other. The biggest difference is in the way they work. Positive displacement compressors confine a mass of air and squeeze it, raising its pressure. Dynamic compressors speed up the air, giving it extra energy that's converted to pressure when it slows down. Another difference between positive displacement and dynamic compressors is their typical capacity. On the average, positive displacement compressors are rated for higher discharge pressures, but the average dynamic compressor tends to have a higher flow rate. So far, we've been talking in general about the two main categories of compressors. Now, within each group, there are several different designs. Now, we'll be talking about each of these designs specifically. We'll see how they work, how they're lubricated and cooled, and how they're controlled. Before we go on, though, take some time to read through Section 1 of your text and work the exercises. When we return, we'll be looking in detail at one type of positive displacement air compressor, the reciprocating type. far, we've talked about compressors in general, and we've seen the two basic categories of air compressors, positive displacement and dynamic. In this section, we're going to be talking about one of the most common types of positive displacement compressors, the reciprocating type. This is one kind of reciprocating compressor right here. It's fairly small, fairly simple model, and let's look and see what this looks like on the inside. In its simplest form, a reciprocating compressor consists of a cylinder, a piston, an inlet valve, and a discharge valve. As the piston moves on the downstroke, the space it occupied is temporarily at less than atmospheric pressure. The higher pressure outside pushes the inlet valve open, allowing air into the cylinder. On the upstroke, the inlet valve closes, and air is squeezed together, raising its pressure and forcing it out through the discharge valve. Downstrokes and upstrokes continue in a cycle, causing compressed air to be delivered to the discharge piping in pulses. On this compressor, I've unbolted the cylinder head so we can see into the cylinder. Now there's the piston moving up and down. As you just saw, atmospheric pressure pushes air in through the inlet valve when the piston moves down. That's the downstroke. And on the upstroke, the piston compresses the air and pushes it out. There, could you hear that? In this example, I'm using my hand in place of the valves. The valves themselves are placed in the head so that each of them opens in only one direction. On the downstroke, when atmospheric pressure is greater than the pressure in the cylinder, it pushes the inlet valve down and lets air into the cylinder. On the upstroke, cylinder's pressure is higher than atmospheric. That pressure differential closes the inlet valve and pushes the discharge valve open. Since these valves are kind of hard to see, let's look at a picture to get an idea of just how they work. Now, this is an inlet valve. It's held in its closed position by spring tension. When the piston moves down, atmospheric pressure overcomes the spring tension, and the valve opens, letting air into the cylinder. The discharge valve is set up opposite the inlet valve. When the piston moves up, it raises air pressure inside the cylinder, making the spring compress, and the valve opens. Now, there are several types of reciprocating compressors. They're categorized by the number of cylinders, number of stages, according to whether they're single-acting or double-acting, and their layout. This compressor is a single-cylinder, single-stage, single-acting, vertical reciprocating compressor. Now, let's see what that means. A pipe connects at the discharge point directly to the receiver. Now, that's the case on any kind of single-stage reciprocating compressor. On a two-stage compressor, the discharge pipe leads to another cylinder, where a piston compresses the air again, raising its pressure even higher. On a three-stage compressor, there would be a third cylinder, with an even higher discharge pressure. There are single-stage compressors with more than one cylinder, but each cylinder discharges directly into the receiver. Reciprocating compressors are also categorized as single-acting or double-acting. Now, this is a single-acting compressor because there's only one inlet valve and one discharge valve. On a double-acting compressor, there's another set of valves right down here. On an upstroke, air is drawn into the bottom of the cylinder, while any air that is in the top of the cylinder is compressed. Then on the downstroke, the air that was just drawn into the bottom of the cylinder is compressed, while air is drawn into the top of the cylinder. There's one more way of classifying reciprocating compressors, and that's by their layout. Now, this compressor has one cylinder pointing straight up. That's called vertical layout. If the cylinder is pointing to the side, it's called horizontal. Two-cylinder compressors can be laid out with both cylinders vertical, with both horizontal, with two cylinders in a V shape, or with two cylinders in an L shape. So we've got 4 different ways to categorize reciprocating compressors. They can be single cylinder or multi-cylinder, single stage or multi-stage. They can be single acting or double acting, and they can have their cylinders laid out vertically, horizontally, in a V, in an L, or in a combination of these types. The layout of a compressor doesn't have a lot to do with its operating characteristics. It has more to do with the space that the machine has to fit into. But the other 3 categories do make a difference in flow rate and in discharge pressure. Now, a single cylinder, single acting, single stage compressor's the simplest type, and it's also the cheapest. But if you need a higher discharge pressure, often the best thing to do is to go to a 2-stage design. The second stage raises the pressure before air enters the receiver. A single stage, single acting compressor can't deliver much more than 250 psi. Now that's about 1750 kilopascals. But multi-stage compressors can generate up to 60,000 psi, 420,000 kilopascals. If you need more flow, you'd use either a double acting or a 2-cylinder compressor. Now either of these would double the flow rate if operating speed remained the same. If size is a major consideration, you'd go with a double acting type because it's more compact than any compressor with 2 cylinders. With double acting or multi-cylinder compressors, you can get flow rates of up to 6,400 cubic feet per minute, equal to 181 cubic meters per minute. Now we're going to move on now and take a look at a compressor that's a little more complicated than any we've seen so far. We'll identify it according to the categories we've just discussed. Now this is a 2-cylinder, 2-stage, double-acting, L-shaped compressor. Let's look at a picture of the inside and see why it's classified that way. As you can see, this compressor has 2 cylinders. The discharge from the vertical cylinder is connected to the inlet of the horizontal cylinder. That means it's a 2-stage compressor. You can tell that each cylinder is double acting by looking at the arrangement of the valves. This cylinder has 2 inlet valves and 2 discharge valves. When the piston moves up, the upper discharge valve opens, and when the piston moves down, the lower discharge valve opens. As far as the layout's concerned, it's easy to tell that this is an L shape. One of the cylinders is vertical and the other is horizontal. Now let's take a look at the airflow through this compressor and see how all the different parts work together. Before air enters the compressor, it passes through an intake air filter. The filter keeps the abrasive dust and other impurities from damaging the piston and cylinders. Air then flows into the first stage cylinder through its 2 inlet valves. On an upstroke, air enters through the lower inlet valve and exits through the upper discharge valve. On a downstroke, air enters the upper inlet valve and leaves through the lower discharge valve. Compressed air leaving the first stage then goes into the intercooler. It's just like an aftercooler, but it reduces the temperature of the air before it enters the second stage. There's also a moisture separator to trap any condensation due to cooling. Since the air is already compressed, the second stage cylinder doesn't have to be as large as the first stage cylinder. The smaller piston takes compressed air from the first stage and compresses it again, raising its pressure even higher. This cylinder is also double acting. On a downstroke, air is being drawn in through the left-hand inlet valve and being discharged through the right-hand discharge valve. On an upstroke, intake and discharge are reversed. When air leaves the second stage, it's been fully compressed. From the second stage cylinder, it flows to an aftercooler, where cold water cools the air before it's transferred to the receiver. Cooling has again added drops of condensation to the air. It's passed through a moisture separator. The flow of air is directed into a tight spiral. Water droplets are thrown out by centrifugal force and run down the sides of the vessel to a drain. The air flows from the moisture separator directly to the receiver. The air's now been compressed, cooled, and dried. We've been talking about reciprocating compressors, compressors with pistons and cylinders. We've seen a couple of different kinds, all the way from this single cylinder, single stage, single acting, vertical type, to the more complicated two-cylinder, two-stage, double acting, L-shaped type. We've seen how their valves work, how the air is actually compressed, and we've looked at the filters, coolers, and moisture separators that are important accessory equipment on these as well as many other kinds of compressors. Now, in a few moments, we'll go on to take a look at some other types of positive displacement compressors. We'll see some of the similarities and differences between each of the different kinds. But before we do, though, take a few minutes to work through Section 2 of your text and discuss the material we've covered so far. If you have any questions, ask your instructor before we continue. We've been talking about one specific kind of positive displacement air compressor, the reciprocating type. That is, compressors with cylinders and pistons. Now, we're going to be talking about a couple of different kinds of positive displacement compressors now. Rotary screw and sliding vane compressors. We'll see what they look like, how they work, and we'll talk about the accessory equipment that keeps them operating efficiently. We'll start with the rotary screw compressor. Inside the casing of a typical rotary screw compressor are two rotors. A main rotor with 4 lobes and a secondary rotor with 6 grooves. Air enters the casing when a groove passes the inlet port. The air fills up the entire groove. As the rotors turn, one lobe of the main rotor meshes with the air-filled groove, forming an air pocket. More rotation causes the air pocket to get smaller as the main rotor rolls farther into the secondary groove. The air is squeezed down toward the end of the groove. When the far end of the groove passes the discharge port, the compressed air is released into the discharge piping. Rotary screw compressors come in 2 different types, dry and wet. The dry type is not oil lubricated. It depends upon a set of timing gears to synchronize the 2 rotors and maintain a slight clearance between them. Since the 2 rotors don't actually touch, they're subject to very little wear. Now, the wet type rotary screw compressors have no timing gears. The main rotor drives the secondary. Oil is sprayed onto the rotors to maintain a film of lubricant between them. The oil in a wet type rotary screw compressor serves 3 purposes. It reduces wear to the rotors, it helps seal in the air, making the compressor more efficient, and it cools the compressor and the air inside it. It takes a lot of oil to do this, gallons of oil every minute. So the air that leaves the compressor has quite a bit of oil mixed in with it. Too much oil tends to gum up air-powered equipment. So before we can use the air, we have to remove the oil from the mixture. For that, we use an oil separator. An oil separator works by forcing the air through a series of baffles or vanes. The air is deflected by the baffles and flows on. But the oil, being denser and heavier, strikes the baffles and falls down to the sump to be recirculated through the compressor. The small amount of oil remaining in the air is removed by passing the air through a fine wire mesh screen before it goes to the receiver. Both wet and dry rotary screw compressors deliver cool, dry, oil-free air to the receiver. The difference is the kinds of accessory equipment that each type needs. The wet type needs an oil separator, a sump, and an oil pump. Many dry types use a water jacket to cool the air and a moisture separator to remove condensation. The next kind of compressor we'll talk about also comes in both wet and dry models. It's the sliding vane compressor. Some are oil lubricated, Those require an oil separator. Dry-type sliding vane compressors often use water jackets and moisture separators. Let's go on then and take a look at the sliding vane compressor. Inside the casing is a cylinder that's fitted with a single rotor. It's mounted off-center so that there's a crescent-shaped space between the rotor and the casing. The rotor has a number of slots around its circumference. Now each slot contains a vane that's free to slide back and forth along its groove. Let's see how the whole thing looks in action. As the rotor spins, centrifugal force makes the vane slide outward against the inside of the casing. Each pair of vanes forms a separate air pocket. Large pockets at the top of the crescent and small pockets at the bottom, where there's least clearance between the rotor and the casing. Air enters the compressor through an inlet port at the top of the crescent and flows into the largest air pocket. As the rotor turns, the air pocket gets smaller. The trapped air is compressed by squeezing it between the rotor and the casing. Compressed air is discharged when the air pocket's been reduced to its minimum size. Both of the compressors we've seen in this section, the rotary screw and the sliding vane, are positive displacement compressors. They work by trapping a quantity of air and squeezing it down into a smaller space. The rotary screw type squeezes the air between a lobe on one rotor and a groove on the other. The sliding vane type squeezes the air between the rotor and the casing while the air is contained within a pair of vanes. Now in the next section, we'll be talking about two different kinds of positive displacement compressors, the liquid ring and the rotary blower. Now, although they don't look much alike, they both use the same principle of operation. They trap a quantity of air and squeeze it together, raising its pressure. We'll be back to take a look at these compressors in a few minutes. But before we go on, stop and read through the section 3 of your text for more information on rotary screw and sliding vane compressors. Work the exercises, and then ask your instructor about any questions you might have. Up to this point, we've talked about 3 different kinds of positive displacement compressors: reciprocating, rotary screw, and sliding vane. Now in this section, we're going to cover the last 2 kinds of positive displacement compressors: the liquid ring compressor and the rotary blower. Now as you'll see, these 2 compressors are very different from the types we've covered earlier. And I guess the best way to show you how they're different is to take a look inside and see just how they work. We'll start with the liquid ring compressor. Inside the casing of a liquid ring compressor is a rotor with a number of blades and an inlet port connected to the inlet pipe and a discharge port connected to the discharge pipe. The rotor and the ports are positioned off-center in the casing so there's more space above the rotor than there is below. The casing's partially filled with a flow of liquid, usually water. When the blades spin, the water's pushed outward by centrifugal force, forming a continuous liquid ring around the rotor. The water seals off air pockets between the blades, forming large air pockets near the inlet port and small air pockets near the discharge port. Air enters the compressor through the inlet pipe, which leads to the large inlet port near the hub. Air from the inlet port flows into the largest air pockets and is trapped between the rotor blades and the ring of water. As air travels around, the ring of water squeezes it into a smaller space. After entering the discharge port, the compressed air flows out through the discharge pipe. In some ways, this is the simplest of all compressors. The rotor is the only moving part. Because of the off-center arrangement of the rotor, water acts as a piston to compress the trapped air. The constant flow of water also cools the compressor, so no additional cooling's needed. However, moisture separators are required to remove the water that's picked up by the compressed air. The liquid ring compressor, like all other positive displacement types we've seen so far, compresses by trapping air in an enclosed space and reducing the volume of that space. The next type of positive displacement compressor we'll discuss, the rotary blower, works a little differently. It does trap a quantity of air and squeezes it together, but it does it without reducing the volume of the space. Instead, it packs more and more air into the space, in effect, using more air to squeeze the air that's already enclosed. Let's take a look inside a rotary blower, and you'll see what I mean. A rotary blower has two figure-8 shaped impellers inside the casing. A set of timing gears, not shown here, keeps the lobes rotating in sync in opposite directions. There's a slight clearance between the lobes so that they never actually touch each other. Air enters the casing from below. When a lobe passes the inlet port, it traps air and transfers it to the discharge side. As the lobe continues to rotate, more air is packed into the space. When pressure in this enclosed space is greater than receiver pressure, compressed air flows through a check valve further along the discharge piping. We've already mentioned one of the major differences between the rotary blower and other positive displacement compressors. The rotary blower doesn't reduce the volume of the trapped air. Instead, it packs more air into the upper part of the casing and the discharge piping, raising the pressure. But there's also another major difference. This compressor is commonly called a blower because of its low discharge pressure, typically not more than 15 psi, or about 105 kilopascals. Now, this is quite a bit lower than the typical discharge pressures of the other compressors we've seen. If a higher discharge pressure is required, then several blowers have to be hooked in series. The other compressor we've seen in this section, the liquid ring type, is also very different from other positive displacement compressors. It's different because water acts to squeeze the air into a smaller space. Its other main difference is that it has only one major moving part, the rotor. That makes it the simplest and the most trouble-free of all positive displacement compressors. Keep these differences in mind as you read Section 4 of your text. It has more detail on the components and the operation of liquid ring compressors and rotary blowers. Those are the last two positive displacement compressors that we're going to talk about. When we return, we'll be covering two kinds of dynamic compressors, centrifugal and axial. In the meantime, study up on positive displacement compressors and ask your instructor about any questions you have concerning their construction and their operation. Dynamic compressors work on an entirely different principle than the compressors we've seen so far. All the compressors we've discussed in the last few sections were positive displacement types. They trap a mass of air and compress it by squeezing it into a smaller space. Dynamic compressors are different. They compress air by accelerating it. The fast-moving air is then converted to high-pressure air by slowing down the flow, and we'll see how that works in a minute. There are two basic kinds of dynamic compressors, centrifugal and axial. Now, we're going to take a look at each of these different kinds and see how they work. To start, let's look at a centrifugal compressor. The only moving part in a centrifugal compressor is the impeller. A shaft connects it to a motor or another prime mover so that the impeller spins around during operation. In the center of the impeller is a set of small blades around an opening called the suction eye. When the impeller spins, these blades draw air into the compressor. Around the outside of the casing is a wider section called a diffuser. Following the diffuser around leads us to the volute, a continually widening discharge pipe. Now let's look at a simplified version and see the parts in action. If we look inside the impeller, we can see that it's composed of several large curving blades. As the impeller turns, air enters the suction eye and is spun outward by the rotating blades. This is how the air picks up speed. The fast-moving air is pushed around the circumference of the casing till it reaches the volute. Here, where the pathway gets larger, is where the air begins to slow down. This increases the air's pressure. Let's see just why this pressure increase takes place. This apparatus will help me demonstrate what actually happens in the volute. Now we're going to blow compressed air through the thin tube and into the wide one. We'll measure the pressure on each side with these columns of water. Now watch as I blow through this tube on the gauge on your right. You see, any increase in pressure will cause the water level to rise. The higher the pressure, the higher the water level will be. Now I'm going to hook one hose to an output on the thin tube, and it will register on the gauge on the right. And we'll hook a hose to the wider portion, and the pressure will register on the gauge on the left. By comparing the water levels in each of these columns, we'll be able to see on which side the pressure's greater. Okay, let's start up and see what happens. As you can see, the water level's higher on the side of the wide tube. Pressure has increased as air has moved from the narrower space to the wider one. Pressure increases in the volute of a centrifugal compressor. As air slows down in this widening space, it pushes outward, raising its pressure. Both kinds of dynamic compressors raise the pressure of air by speeding it up, then slowing it down, causing its pressure to increase as we saw in the demonstration. But centrifugal and axial compressors accomplish this in different ways. Centrifugal compressors spin air out and around to the diffuser and the volute, where flow rate drops and pressure increases. Axial compressors have rotating blades that push the air down the length of the casing. Fixed, non-rotating blades are used to slow down the flow and raise the pressure. Let's see what an axial compressor looks like on the inside. An axial compressor has a tapered shell and fixed stator blades, and a shaft with spinning rotor blades. Air enters the compressor where the shell is widest. The rotor blades act like fans that push the air down the length of the compressor. Now, since the stator blades don't move, they direct the air flow and provide some resistance that slows the air down, causing pressure to increase at every stage. After the last set of stators, where pressure is the greatest, the compressed air flows out into the discharge piping. Both types of dynamic compressors, centrifugal and axial, are typically used for high flow, low pressure applications, like blast furnaces or processes where a flow of air is used to separate materials of different densities. Large axial compressors are also used in wind tunnels for testing the aerodynamic characteristics of aircraft. These are mostly constant demand, constant flow applications. Typically, centrifugal and axial compressors aren't equipped with receivers, because when you need flow, you turn the compressor on, and when you don't, you turn it off. There's no need to store up compressed air. They do usually have aftercoolers and moisture separators, because like other compressors, they heat up the air, and when you cool the air, you get condensation. Well, now we've seen how both kinds of dynamic compressors work, and we've also talked about how they're alike and how they differ from each other. The axial compressor is the last of the 7 types that we're going to be talking about. We've seen how each type works, looked at accessory equipment that some of the compressors need to operate at full efficiency: cooling systems, moisture separators, lubrication systems, and oil separators. However, there's one major item that we still have to discuss, and that is pressure control. That's the subject of the next section. Before we go on, though, study Section 5 of your text and make sure you've learned everything you need to know about dynamic compressors. to this point in the program, we've been talking about how compressors work. We've seen 7 different types. First, we looked at positive displacement compressors: reciprocating, rotary screw, sliding vane, liquid ring, and the rotary blower. In the last section, we saw the 2 types of dynamic compressors: centrifugal and axial. When any of these compressors are hooked up to an air system, they have to be regulated to maintain a certain discharge pressure and flow rate. A compressor's output has to match the capacity of the system. If the pressure or flow rate is too low, the system can't operate at full efficiency. Now, the same is true if the pressure and the flow rate are too high. That's why we have controlled systems, to match a compressor's output to the demand of the total air system. In extreme cases, a compressor that's created too much pressure could make a receiver or a pipe explode. We're going to be talking about several different kinds of control systems. The first 2 types we'll discuss are applicable to any kind of compressor: on-off cycling and speed control. The simplest way to control pressure is an on-off cycling control to shut down the compressor when the pressure gets too high, and to start it up again when pressure decreases. That's exactly what happens on this compressor. There's a pressure sensor here. When it senses normal pressure, it opens a circuit and stops the motor. When pressure drops to a lower value, the circuit closes and the motor starts up again, so it'll cycle on and off. As air is used, the compressor will keep filling the receiver. When air is not being used, the compressor will fill the receiver up to full capacity, then shut off. This kind of on-off cycling control is the most common of all pressure controls, especially on small compressors like this one. There are some other ways to do it. One alternative is to vary the speed of the motor. As receiver pressure increases, a pressure-sensing device slows the motor down so the compressor won't put out as much air. When pressure starts to drop, the device makes the motor speed up to match the new demand. As I said before, on-off cycling or speed control can be used with any compressor, positive displacement or dynamic. But there's another group of controls that's only effective on positive displacement compressors. That is, inlet valve unloaders, clearance pockets, and air-controlled inlet valves. We'll start with inlet valve unloaders, then go through the others one at a time. To begin with, an inlet valve unloader is used only on reciprocating compressors. And here's how it works. The receiver has a pressure sensor. When it senses normal pressure, it opens a valve sending high-pressure air down a line to the inlet valve. The air pressure holds the valve open. On a downstroke, air enters the cylinder normally, but on the upstroke, air flows back out the inlet valve, so the piston isn't compressing the air. In this unloaded position, the motor and piston continue moving at their normal speed, but no compressed air enters the discharge piping. When a reciprocating compressor is operating with the inlet valve unloaded, you've effectively stopped the flow. Sometimes, though, it's not necessary to completely shut down the flow of air into the receiver. You might want to just slow it down instead. When that's the case, you can use a reciprocating compressor with clearance pockets. This chamber is the clearance pocket. It's an airspace that's connected to the cylinder, but it's isolated by this normally closed valve. The valve's operated by an air line that goes to the receiver. When receiver pressure reaches a certain point, pressure in the air line opens the valve, connecting the clearance pocket to the cylinder. Now, this creates an extra airspace in the cylinder. So on the discharge stroke, only part of the air in the cylinder is forced out through the discharge valve. The rest of it stays in the clearance pocket. So the compressor's flow rate has been reduced. Some reciprocating compressors are made with as many as 4 clearance pockets. The more pockets that are open, the more the flow rate's reduced. That way, the output of the compressor can be matched to the demand of air, so the receiver can maintain a constant pressure. Inlet valve unloaders and clearance pockets are both control devices for reciprocating compressors. They both depend on valves operated by receiver pressure. Now, on sliding vane and rotary screw compressors, another kind of air-controlled inlet valve is often used to reduce flow when receiver pressure increases. Let's see how it works. The valve itself is within the inlet pipe. It's connected by an external mechanical linkage to a piston in the cylinder. The piston's normally kept in the up position by a spring. An air line connects the top of the cylinder to the receiver. Now, when receiver pressure increases, air pressure pushes down on the piston, overcoming the tension of the spring. Now, this partially closes the inlet valve, reducing flow through the compressor. When normal consumption lowers receiver pressure, the spring pushes the piston back up, opening the valve to increase airflow. All of the devices we've seen so far are common to positive displacement compressors. They sense pressure and react to keep it within normal operating limits. With dynamic compressors, we have different problems. Let's look at this graphic of a centrifugal compressor and see what happens when we get too much pressure in the discharge line. Since there's no valve separating the volute from the discharge pipe, the impeller just keeps packing air into the pipe. When pressure gets above a certain point, air will try and flow backwards from the discharge pipe into the compressor. Now, when the impeller's spinning this way, the air's trying to flow back against it. You're going to get a lot of turbulence inside the compressor. This problem is called surge. The air comes out in pulses. The impeller will be making thumping noises, and the whole compressor will vibrate. Although nothing's likely to burst from overpressure, the vibration and mechanical strain can cause serious damage to the compressor. All dynamic compressors have to have some way to control surge. The most important consideration is to keep a constant flow going through the compressor. One way to maintain flow is with a flow control and a blowout valve. Under normal conditions, the flow controller keeps the air moving through the volute and out through the discharge piping. However, when pressure in the discharge piping increases, air begins to get backed up. It can't keep flowing through at the same rate. To divert some of the air, the flow controller opens a blowout valve. Opening the valve allows some of the air to escape, maintaining a constant flow through the compressor. Blowout valves help keep centrifugal and axial compressors from being damaged when their flow rates are too low. They're needed when the demand for compressed air is suddenly reduced. The air has to go somewhere, so if the system's already at full pressure, the air is simply released. However, dynamic compressors can also be damaged when there's too great a demand. For example, if there was a major leak in an air system's piping, system pressure goes down drastically. Now that calls for more flow through the compressor. When the flow rate gets too high, you've got two potential problems. First, when flow increases, pressure drops. If pressure in the discharge piping is even momentarily higher than pressure inside the casing, this can damage the compressor due to a condition very similar to surge. Secondly, when demand for flow suddenly increases, the motor has to start putting out more horsepower and draws more current. The problem is, if that current draw exceeds the motor's maximum rating, wires will start to heat up and the motor may burn out. What we have to do then is to provide some resistance to airflow so that the motor draws only a normal amount of current. For that, we use an inlet air throttle. The inlet air throttle is a butterfly valve within the inlet piping. The control unit up above receives a signal from the motor when it starts to draw too much current. The unit then partially closes the butterfly valve, restricting the intake airflow. If demand is still too great, the valve will close completely, effectively shutting down the compressor. Inlet valve throttles on dynamic compressors are typically called into play only when there's a major leak in the system it supplies. For example, if an airline burst, the sudden increase in demand would cause the valve to close down. In an extreme case like this, the compressor would be completely shut down until the piping was repaired. Normally, though, pressure isn't allowed to get high enough to burst a pipe. That's because almost every compressed air system, no matter what type of compressor is used, has an emergency backup, a safety valve that allows pressure to escape when it gets up to potentially dangerous level. Safety valves are located downstream from the compressor discharge. Normally, they're held shut by spring tension. But when too much pressure builds up in the discharge line, it overcomes the spring tension and allows air to escape to the atmosphere. When pressure drops back to a safe level, it's no longer strong enough to hold the valve open, so the valve shuts, cutting off the flow of escaping air. To sum up this program, we've talked about 7 different kinds of compressors. We've seen how they work, how they're cooled and lubricated, and how they're controlled to maintain normal pressure and prevent surge, overheating, and overpressure accidents. Throughout the tape, we've been talking about compressing air. That's what most compressors are used for. But any of these compressors can be used to compress other gases, oxygen, nitrogen, or even natural gas. Compressors can also be used to draw a vacuum. If their intakes are connected to an enclosed vessel, they'll draw air out of that space, so the pressure in the vessel will be less than atmospheric pressure. Where you work, you probably find compressors being used for many different kinds of jobs. Take a look around and see what kinds of compressors are used for each application. The background you've gotten here should help you understand how and why they're used the way they are. That understanding will help make you a better mechanic.